Hi everyone! This week we have two requested topics for Anova. The first topic is how to get the number of replicates, or little n, from Anova tables when you don't have equal observations. The second is why one-factor versus two-factor Anova tests turn out different in terms of what comes up as significantly different. The first I can address really quickly. It's not possible to get n for unequal observations from an Anova table. You actually have to look at your full data set to do that. And this is very disappointing news for some of you because you say, oh, well, how am I going to get that from the table? And what if you ask that on the test? Well, first off, I would never ask that on any kind of assignment because it's not a fair question. You have so many potential answers, and we'll take a look at that in just a second. As for the second topic, that has to do with your error degrees of freedom and how the sum of squares and mean squares turn out because of the changes in your error degrees of freedom. It can shift your F values, which means you have differences in terms of significance. So we'll take a look at that as well. But first off, let's see why exactly you can't figure out the number of observations from an Anova table if you don't have equal observations. Here's a sample Anova table. Here is our formula for the error degrees of freedom if we have equal observations. If we don't have equal observations, we cannot use this formula because we don't have constant n between A, B, and AB. It could be anything that gives us our total degrees of freedom, our total observations. So let's take a look at this. Here in this table, A is 2. We have 2 different levels for A. B is 4, so we have 4 different levels for B. That means AB degrees of freedom are 3, because that is A minus 1 times B minus 1. And so we know our total observations here has to be 32 because our total degrees of freedom is 31. And that means by subtraction, 31 minus 1 minus 3 minus 3, that gives us 24. So we have 24 error degrees of freedom. And somehow that gets split between 32 observations. But how do you know if you don't have unequal replicates per treatment what little n is? How many of those replicates we have? Because if you think about it, we could have possibly 1 replicate for each level of A, and then up to 27 replicates for each level of B. If we know we have 2 replicates for each level of A, then we can have up to 25 replicates for each level of B. And you're saying, well, wait a minute, no, that's not possible that we have 27 replicates for B if we have 1 replicate for each of A. But yeah, we do, because if you think we have 2 for A, so that's 30 replicates left over. And then if we've got 27 plus 1 plus 1 plus 1, because we are terrible scientists and we're very bad at replication, that gives us 32 observations overall. Same thing for if we have 2 replicates for each of A. That gives us 4 total replicates there. So we have 28 more observations left over, which could potentially be 25 plus 1 plus 1 plus 1, because again, we are terrible scientists and we're very bad at replication. Both of those scenarios give us the total number of observations we have, and we don't have any information from this table to tell us whether or not we're correct. So, if you have unequal observations, there is no way you can pull the number of observations for each particular treatment out of your Anova table. You're going to have to go back to your original data set and take a look at it there. And so if you're thinking about the candy chewing problem we have and going, well, why does this not work out? Why do we have to back out error degrees of freedom from our total on our others? That's why. Because your formula right here breaks down as soon as you do not have equal observations for each particular treatment. And that's why you can't use this formula, and if you try, you're going to get something very, very strange for your error degrees of freedom compared to everything else. So please don't use that formula if you've got unequal observations. You have to figure it out from your data. On to topic 2. Why do your Anova tests come out differently sometimes if you've got 1 versus 2 factor ANOVA? Shouldn't it be just you have significance or you don't? No, sorry, that's not the way it works. And actually you can get yourself into big trouble statistically if you're making that assumption and you're just sort of adding things onto your analysis. Your analysis will change depending on what you're analyzing. So be really careful if you're analyzing any kind of data sets. Let's take a look at 1 factor versus 2 factor ANOVA for a completely fictional data set. The numbers are very nice and round, so the math is really easy and it's easy to follow. You would never see anything with perfectly round sum of squares like this. But let's make sure our sum of squares carry through for 1 to 2 factor so that we can make a comparison of our sum of squares, our degrees of freedom, our mean squares, and our F value. So we will take a look at factor A first. If you go through this table, yes, the math all works out, and that gives you an F value of 4.0. The critical value for alpha equals 0.05 from our F tables, given that N1 is 3 and N2 is 8, is 4.07, and that means we cannot reject our null right here because 4.0 is less than 4.07. We're not beyond our rejection criteria yet, so we can't reject. For B, on the other hand, we have an F value of 6, and that means we actually can reject the null because 6 is greater than 4.07. We can use the same F alpha and N1, N2 value for this particular test because our degrees of freedom are the same. So that's great. Okay, now let's look at our 2 factor ANOVA table. Here we see the sum of squares for A and B are the exact same as they were in the 1 factor. So are our degrees of freedom because we didn't really change anything with A and B. We do have our interaction term added in. So we have sum of squares and degrees of freedom for that. And now we have our error term. And because we did more replicates, because this is now a 2 factor instead of a 1 factor, we've got a higher total degrees of freedom and a higher error degrees of freedom. Our error sum of squares is different as well because, again, we've got more observations, and so that means there's more room for experimental error. And it's not necessarily that you did anything wrong in your experiments, just the more observations you do, the more error is going to start piling up because error is just sort of inherent to every measurement you do. You're going to have some kind of measurement error because you're making a sample and you're not looking at the entire population. So that's why your error sum of squares went up. Here, our mean square is the same for A and B. We have a mean square for AB as well, and we have a mean square for error, but if you remember back before, it was 25, now it's 100. Because it's 100, we have different F values. So our error sum of squares went up, our error degrees of freedom went up, and our error mean square went up. This is not always the case, but it's what happened here, and it's affecting all of our F values. It's also affecting our critical values for F alpha. So because we have N2 is 32 now, instead of 8, that will change our critical value. It is 2.90 for A and B, and 2.19 for AB. The reason we've got 2 different F values for comparison is because our degrees of freedom for AB are different from A and B. So here N1 is 3 to give us our F value of 2.9. Here N1 is 32 to give us our F value of 2.19. So when you're making these 2-factor tables, be really, really careful about looking up your F alpha values. You may have up to 3 different F alpha values for a 2-factor ANOVA table. You guys looked out in the homework problem, all of the degrees of freedom here were 1. So you had 1 F alpha value. So make sure you're making that distinction between your degrees of freedom for N1 versus N2 and that you've got the correct N1 value for your F alpha. Having said that, let's take a look at our F0 values versus our F alpha values, and you can see that even though we've got different F alpha values here, we are below those F alpha values, so we can't reject the null. If you look at B, B is no longer significantly different. There are no significant differences because of B anymore, because now we have more mean square error, and that is changing our F value for B. And so that is why, because our error is higher here, we say, well, we're not sure enough to be able to reject that null. We are still in our null hypothesis because we had too much error to see if there was a significant difference. So that is why two-factor ANOVA results can come out different than one-factor. It's all in what goes into this particular F calculation. And so if your error starts going up, your significance is going to start dropping. So hopefully that clears up figuring out unequal observations. The answer is unfortunately you can't, and why one-factor and two-factor ANOVA analyses can come out different. Now, because they can come out different, there is the potential to cheat and say, well, I know that if I add this thing in, my error sum of squares is going to be too high. That means that mean square is going to be too high. That means my F value is going to drop and nothing's going to be significant. I don't want that. I really want to reject this null. That is not quite data falsification, but it is playing with statistics in a way that you shouldn't. So you have to run your data set as is, and however that null decision comes out, that's what you take, because that's what the statistics are telling you. So sometimes it's really tempting to play with your data set, knock out some of that error so you pick up significant differences, but that's really bad science. So please don't do that in any kind of statistical analyses you run. Just let the data tell you what it has to say, and don't try to make it say what you want it to.